Good morning and welcome to our today's lesson. We want to talk about Newton's laws of motion and find out whether force has anything to do with how a body reacts to different changes in the parameters of its motion. Now, I will want us to always recall the effects of force on a body in general. We have really discussed them, we have expounded them, but just as a reminder, I would like to remind you the 4 effects of force on an object. Number 1, it slows down or even stops a body it could start or accelerate a body it could change the shape or even direction. Now, there are several parameters that we looked at when we were discussing linear motion that are associated with a body in motion, and one of them was velocity. The other one was acceleration. Onto our list, we could also add retardation. And of course, for all this to be achieved, time factor has also to be put into consideration. Now, of our interest in this chapter will now be how force slows down or even stops an object, how it could start or accelerate the body in motion, and how these parameters could also be altered in the course of movement of that body. Now, basically, there are 3 laws. There are 3 laws of motion that we call the Newton's laws of motion, and they work under the guidelines of the effects of force. In other words, they govern how the force is going to affect the state of motion of an object. Now, let us look at first law. The first law of motion. This law is also called the law of inertia. The law of inertia is our first law. And we have agreed that when a body is acted upon by balanced forces, when the forces acting on a body balance each other, that there will be a constant state of motion of that body. Velocity will be constant, and therefore we could be justified to say that acceleration is 0. Now, that is all what the first law of motion is all about. And I will begin by stating it even as we expound it. And it states that a body remains in its state of motion unless a body is acted upon by an external force, its state of motion, will be constant. It will not change until an external force acts on that particular body. Now, a body could be at a state of rest, for example, or it could be moving at a constant speed. Now, assuming that no force acts upon the object, then its state of motion will always remain the same. That is what we refer to as inertia. Inertia. That a body, there is an inbuilt reluctance by a body to change in its state of motion. So if a body is at rest, it tends to remain at rest, and when a force acts upon it, it will resist the change in state of motion. Now that is what we call inertia, that reluctance to change in state of motion. Now, for example, if you board a bus that is in motion, and then it is halted suddenly, you are pushed forward, which means you are resisting your change in your state of motion. Remember that even yourself, the passengers on the bus, you are moving at the speed with which the bus is moving. Therefore, if the bus is brought to a halt, you will be pushed forward. In other words, you will continue moving even if the bus stops. That is what we call inertia. Now, there are factors There are some two important factors that affect inertia, or that will inform this reluctance in change of direction and even state of motion of an object. We call them factors affecting inertia. I want to look at them. Factors affecting inertia. And we have about two. Number one is the force Now we have said that the body does not change until an external force acts on it. Therefore, this force must have a take in as far as inertia of an object is concerned. And the greater we are saying that the greater the force applied, remember we said a body in constant state of motion has all its forces balanced. Now we are introducing another force, an external force, and we expect it to alter the balance that we had. Now, the greater the force we are going to apply, the higher the effect it will yield on our state of motion of the object. Factor number 2 is the mass of the body. Remember we said that mass of a body is always constant. Now, the force, say, of 20 newtons can produce a bigger effect on an object of smaller mass as compared to that of big mass. Therefore, what we are saying is that the higher or the greater the mass of the body that we are considering, the higher its reluctance will be to the change of state of its motion. The higher the reluctance, it will yield to the state of change of its motion. Large masses, therefore, require large forces so that their change of motion state can be realized. That the higher the mass, the higher the force we shall require to apply in order for us to alter the state of motion of the body. Now, this one is generalized, or we are generalizing on any body depending, or if we hold other factors constant, then the force and the mass of the object are going to inform how we are supposed to go about changing the state of motion of the bodies. Now, how important is that concept to us today? Because whatever knowledge we have has to be applied in our lives in one way or the other. Let us look at the applications we have. Now, applications of inertia. we have to be informed that this reluctance is there. Therefore, we have to take caution. We have to be prepared to face the result of whatever this reluctance is going to yield. Number one is to ensure that all our locomotives are fitted with seat belts. For example, buses, trains, aircrafts, and the list can continue. We fit them with seat belts so that in case of sudden breakage of these locomotives, if you bring it to a halt, you will expect that the external force that will be applied on the brakes to make sure that the locomotive comes to a halt is going to be large. Therefore, our passengers will have that inbuilt reluctance to continue moving even as the locomotive comes to a halt. We have to make sure that they are fastened with seat belts so that when they are pushed forward, there will not be a fatal kind of collision. Number two is on aircrafts. Now, when an aircraft is airborne and moving at a constant velocity at a given altitude, we have about 4 forces acting on our aircraft. Number one is what we call the weight. This is the weight of the aircraft and the passengers. It acts downwards. Now, we also have the lift, which acts upwards to balance the weight. We also have the thrust, will be acting forward. And finally, we have the drag, which can also be called air resistance. And this one acts backwards. Now, for us to achieve a common velocity at a given altitude, the 4 forces are supposed to balance each other. Therefore, the net force acting on our aircraft, when you resolve the 4, should be 0. It should be 0, and that way we can achieve a constant velocity at a given altitude. We could consider accelerating our aircraft, for example, because at some point you would desire to move faster. Therefore, our thrust, which is the force this is the weight, this is the drag, the lift, and finally the thrust. We are saying that they have to strike a balance for there to be a constant velocity at a given altitude. But now we are asking ourselves, suppose we want to accelerate our aircraft, what will happen? It means now we have to break this balance. We have to break this balance, and that one is achieved by increasing the thrust. You increase the magnitude of the thrust. Now remember, we said that force is a vector. It is actually a vector. Therefore, whatever alterations we want to make on our aircraft will happen in the direction of motion or direction of action of the force that we alter. Now, our desire here is to move forward, and therefore we will consider altering the force that will give us a change in that particular direction. You increase the magnitude of the thrust, the balance is offset, and therefore all the forces now are not balanced. Therefore, you have to consider all the directions. If this one increases and the air resistance is constant, then it means we have to do something to the lift all the weight. Therefore, what will happen? The lift will also be automatically increased. The lift increases to re-achieve the balance, and when the lift increases, that means our aircraft is now going to be lifted higher as well as thrusted forward at a faster rate. Therefore, accelerating our aircraft is accompanied by lifting it to a greater altitude. How about decelerating it? If you wanted to decelerate, or you wanted to slow down a bit, what will happen? Now remember, we have no control over air resistance, just like we have no control over the weight, because the weight is supposed to be determined by the contents of the aircraft. Now, we are not altering anything. The number of passengers remain constant. The material that has been used to build our aircraft is also constant. Therefore, whatever forces we have to consider are the lift and the thrust. Therefore, what we will do is that we will decrease we shall decrease the magnitude of not the aircraft but the thrust, and this one is going to be followed by an automatic decrease in the lift. And that way we can achieve another velocity which is actually lower than the first one and at a lower altitude. At a lower altitude. So basically that is how we apply inertia in our daily activities. We want to look at something else we are going to call momentum. Momentum. And we are still on the parameters of motion of a moving object. Remember, here we are considering a linear motion, and our momentum, which we are going to call capital P, is now the product. It is actually the product of mass and velocity. Mass and velocity of an object. The product of the two gives us the momentum thereof. Now, remember we said that mass is a scalar, and mass of any object is constant everywhere. Mass of any object is constant everywhere. Therefore, should we want to change the momentum of an object, what to alter is actually the velocity. Now, we are saying momentum is given by mass, which we are going to call m, and we multiply this by the velocity v of an object. This parameter here is constant everywhere. Constant everywhere, and therefore if we desire to have a change in momentum of an object, we should alter the velocity. How? We can leave our body to move at a constant speed, or we can apply an external force, either to slow or to fasten our body. Both will yield a change in momentum, because momentum is achieved by multiplying mass, which is constant, and the velocity, which we have played about with. But now, let us change, or let us express momentum mathematically, and probably try to come up with units that we can use to express the same. Now, momentum P is given by mass, which we are calling capital M, and we multiply this by velocity V, and we can therefore say that momentum is given by mass, or the product of mass and the velocity. Now, how about the units? Because it being a quantity of measurement, it's got to have some units. Let us try to come up with the units of momentum from mass and velocity. And mass is given in kgs, or kilograms if you may. Then our velocity is measured in meters per second. Therefore, if we multiply the two, what we get is kilograms meters per second, which is actually the unit that we use to express momentum. Therefore, should anybody ask you to give the units of momentum, it's kilograms meters per second. Let us look at some factors that will affect momentum of a body. Therefore, factors affecting momentum. And we have about two. Now, one of them being the mass of the body in consideration. And mass is actually directly proportional to the momentum of a body, because from the formula that we have just derived, momentum is given by mass times velocity. Therefore, increase the mass and you will have increased the momentum. Therefore, the higher the mass, the greater the momentum. We could also look at another factor, which we will call the velocity of the body. And again, this one is also directly proportional is also directly proportional to the momentum of the body. Probably before we go to some numeric examples, I would also like to point out that momentum is actually a vector quantity. That momentum is a vector quantity. Now, from the formula, we have seen that momentum is given by mass times velocity. Now, mass in itself is a scalar, but velocity is a vector. Therefore, the direction of the velocity that we are considering is a factor that we cannot afford to overlook. Therefore, we assume that our momentum will take the direction of the velocity of the object. And for that reason, we say that momentum is actually a vector quantity whose direction is the same as the direction of velocity of the object. the direction of velocity. Let us now look at an example of a problem involving the momentum formula. Now the question reads, a van of mass 3 metric tons is traveling at a velocity of 72 kilograms per hour. So we are supposed to get the momentum of that vehicle. We are supposed to apply the formula to get the momentum of that vehicle. Now, first we look at what the question provides. It provides the mass, which is given as 3 tons. Then we have the velocity, which is given as 72 kilometers per hour. Now, let us go back to our formula. Momentum is given by mass times velocity, and this one is expressed in kilograms meters per second. Kilograms meters per second. That means that whatever we have been given should be in kilograms if it's mass, or meters per second if it's velocity. Therefore, the first step will be to change the mass into kilograms. Therefore, this will be 3 times 1,000. These ones are kilograms. And our velocity will also be changed to meters per second. Now these ones will be meters per second. Now, the mass now becomes 3,000 kilograms. Velocity becomes 20 meters per second. Now we can go ahead and apply our momentum formula. Say that momentum is given by mass times velocity. which will be given by 3,000 kilograms, and this one we multiply by 20 meters per second, 20 meters per second, after converting 72 kilometers per hour to meters per second, and this one gives us around 60,000 kilograms meters per second. 60,000 kilograms meters per second. Could also look at another example. Now we are told that a car is moving at 36 kilometers per hour, and we have not been given the mass of that vehicle, but we are required to come up with a figure that will represent a velocity that should double its momentum. Recall that we said momentum is given by mass and we multiply by velocity. Again, it's good to remember that mass of an object will always be constant. Now let us take a letter, say m, to represent the mass. In this case, we take the mass to be m. Remember that this mass will remain at the beginning, and even after doubling the momentum, the mass will remain the same. So we can take m to represent the mass of that vehicle. We have also been given the initial velocity, which is 36 kilometers per hour. So we change that. 36 kilometers per hour will be changed to meters per second. And this gives us 10 meters per second as our velocity. So let us get the initial momentum. Momentum will be m in kilograms, which is our mass, and then we multiply by 10 meters per second, which is our velocity, and that will give us 10 m kilograms meters per second. Now, we want to double this momentum and then find out what velocity is going to be involved. Therefore, the final momentum will be twice the initial momentum. It will be twice the initial. We want to double it, so twice the initial momentum, which will give us 20 m kilograms meters per second. But now we know that momentum is given by mass and we multiply by velocity. So what velocity will give us this kind of momentum? Now, we said that mass is always constant. So whether in an initial case, whether in the final case, our mass remains m. So now let us make velocity the subject, and this one will be achieved by dividing by mass throughout. We divide by mass throughout, and velocity will be given by momentum over mass, which is going to be 20 mass kilogram meters per second. You divide by the mass, which we took to be m, and these two will cancel. Of course, mass is in kgs, so the units will also cancel, so that now the velocity of our interest will be 20 meters per second. That the initial momentum would be given by mass and the velocity with which the vehicle started the journey. And that one gave us 10 m kilograms meters per second. M because our mass was not given, and now taking it to be a constant, we chose m to represent our mass. Now, at the final point of the journey, the momentum will have doubled, and that means twice the initial momentum, which will be 20 m kilograms meters per second. And if we substitute that in our formula, then the velocity becomes 20 meters per second. 20 meters per second. Meters per second. Let us look at Newton's second law. Newton's second law. Newton's second law. Now, from the first law, we have seen that unless we have an external force acting on a body, then the state of motion of that body is not altered. Now, we want to introduce an external force and see how that one is going to impact our momentum, and probably come up with a second law of motion. So let us consider a body Let us consider a body of mass m, again taking a letter to represent our mass. It's moving with an initial velocity u, which we are going to call u. We want to introduce an external force to act on this body over a time t, so that finally our body accelerates to v. Now, our initial momentum is going to be given by the mass and the initial velocity. The final momentum which we are going to call P subscript F will be given by mass, the product of mass and the final velocity. Now, from the information we have been given, let us look at the change of momentum. And the change of momentum will be the product of the mass and the final velocity. We subtract that of mass and the initial velocity. This one has taken place within some given time we are calling t. Therefore, the change which is realized after subtracting the two figures, the final and the initial momentum, takes place in a given time we are going to call t. Now, the change in momentum is what now we have numerically written as mv minus mu, and this one is also taking place over a time we are going to call t. Now, we look at our right side of the equation and we can factor out m, so that now the rate of change of momentum over time t is going to be given by m into v minus u over t. Now, but from the equations of linear motion, v minus u over t is what we call the acceleration. Therefore, we could substitute the same in our equation, so that now we have the rate of change of momentum being equal to mass times acceleration. Now, clearly, if we introduce a bigger force, now our velocity will have changed a greater deal, and the same case will apply to a smaller force that will result. Acha nianze tu hapo. Sio? The change is realized within a time we are going to call t. Therefore, time t, therefore, the rate of change will be given by change in momentum. which is also equal to mv minus mu. Now, this one should be divided by the time taken to realize the change in momentum. Now, but we can factor out m on the right side so that now our rate of change of momentum will be given by m into v minus u, and this one should be over a time we are going to call t. Now, from equations of linear motion, v minus u over t gives us acceleration, and therefore we could substitute it in our previous equation so that now change of momentum, or the rate of change of momentum, is given by ma. Now, we are also noting that the external force acting on this body is directly proportional to the change of momentum. Therefore, we could substitute our left hand side of the equation with that, and we say F therefore is directly proportional to ma, where m is the mass, a is the acceleration, F is the external force that we introduced. We want to get rid of the proportionality sign. Therefore, we could introduce a constant, say k, then ma. But now from this one, we can call it equation 1. But our force, if now force is directly proportional to the change of momentum, which we are calling ma, then a force of unit Newton, or a force of 1 Newton, should produce a unit change in momentum. A force of 1 Newton should produce a unit change in momentum, and therefore we could be justified to take our k to be equal to 1, so that now if we substitute for k in our equation 1, then F becomes ma. F becomes ma, which is our second law of motion, that a unit force produces a unit change in momentum. Therefore, we could take our k to be 1, and after substituting it, therefore we get our force being equal to mass, and we multiply that by the acceleration of a body, and we are calling that our second law of motion in numeric form. When next we meet, we are going to state the law and even work on examples that will involve the formula we have just derived. Thank you.